Talk of today is reconciling knowledge-based and data-driven AI for human-in-the-loop machine learning. And as you all, of course, know, is that AI is not some recent invention of some marketing department in Silicon Valley or something, but AI is a traditional old part of computer science with many relations to cognitive science. And the first wave, when we look back, has been the wave basically of expert systems. And there, the exclusive focus, the nearly exclusive focus, has been on explicit representations of knowledge, with the advantage that the algorithms are rather powerful and have often provable characteristics. And those of you who remember back, remember that the machine learning researchers at this time have been kind of dominated by the knowledge representation crowd, and that people argued things like, you do machine learning, generalizing over data, this can never be applied in practice, yeah? And now look what we have today. So basically, when the dominance of explicit representation and knowledge representation techniques have been so strong, it has been ignored that large amount of human knowledge is simply not available to inspection and verbalization. This has also been called Polanyi's paradox. How can we know more than we can tell? Yeah, and there is this huge area of implicit tacit knowledge, for instance, perceptual knowledge, where deep learning approaches like CNN are exceptionally successful for object recognition, for instance. But it's also true for highly automated expert knowledge, for procedural knowledge and skills, and for common sense reasoning. So the knowledge engineering bottleneck led to one of the famous AI winters. And then the second wave of AI began. Machine learning became more and more prominent. And nowadays, when we look at practical application and the amount of submissions at conferences, what the topics are there, we have a nearly exclusive focus on data-intensive machine learning. By the way, back in the 1980s, there was also specific hardware, the so-called Lisp machines. Like nowadays, we have these GPU processor hardware from NVIDIA and others. Lots of similarities. But more and more, it is recognized that there are very high demands on the amount and especially also on the quality of data. So basically, the old saying holds garbage in, garbage out, and people recognize that it might be easy to use crowdsourcing to label images of everyday objects, cats, cars, houses. But when you want to have labels for images from medical diagnostics or for industrial quality control, you need high paid experts, highly qualified experts to do this. So maybe we could experience a data engineering bottleneck leading to the next AI winter. So Bamberg is near Nuremberg, by the way, and there the famous Nuremberg funnel was invented, where learning was seen as putting the data in the head, which is obviously not how learning functions when you look at cognitive theories of learning. So there is a nice paper this year in the communications of the ACM from Subaru Kambhampati. Some of you might know him. He is very well known in the domain of AI planning. And in his paper, he used the title Polanyi's Revenge. Remember back the last slides, Polanyi's paradox was, how can we know more than we can tell? And now this leading to the knowledge engineering bottleneck. And now Polanyi strikes back in a way, because recently, as you all might know, this is also the case in psychology and cognitive science. The focus is nearly exclusively on learning from massive amounts of data, even if we have explicit theories and hard-won causal knowledge, right? So basically, in deep learning or in other machine learning approaches, it is simply not true that they are just driven by data. Typically, knowledge is injected there through architectural biases and very carefully manufactured examples. What I like most in the paper of Kambapati is this anecdotal evidence that in industry, practitioners are now ready to convert standard operating procedures into data to learn them back, which is really ridiculous. I think it holds what I already know. I don't need to learn over and over and over again. So please give me the wisdom to be able to discriminate between the things I cannot learn and the things I can and should. Okay. Yeah, so within AI research, more and more researchers over the last at least 4 years recognized that exclusive focus on data-intensive machine learning is not the way to go. So the third wave began. Actually, there was a nice conference in London in summer 2019, where Stephen Muggleton invited researchers for a third wave of AI workshop. And so this third wave of XI, often seen synonymous to explainable AI, XAI for short, more and more is seen as more things than just explainability. So the third wave of AI should focus on hybrid systems, combining reasoning and learning, explanatory systems, making decisions transparent to humans, interactive systems, giving the humans back control, and human-centric. So here, this is just a preview. I will come back later to these different images here. I will now show you some slides about a really old-fashioned approach to machine learning, which I still like very much and use. And then I will talk about explanatory and interactive machine learning and show you some results of our research there. But first, maybe you know this terrible, terrible image about the trade-off between the predictive accuracy and the interpretability of machine learning approaches. This is simply not true in this absolute form. So typically people say, well, you can have high predictive accuracy only with neural networks or other statistical machine learning approaches. For the other stuff like decision trees, you have interpretability, but you can never reach high accuracy. This might be true for domains like end-to-end learning from images, but this is definitely not true when you look at typical data sets based on features, typical tabular data, for instance. And many, many data sets and practical applications are such tabular data. So I recommend the paper of Cynthia Radin, Stop Explaining Black Box Machine Learning Models and Use Interpretable Models instead. It's a really very interesting paper to read. Machine learning is as old as AI research, And as AI research in the beginning, it was interested in computer algorithms which simulate learning like human learning works. So human-like learning was very much in the focus for many of the early AI researchers. And I'm sure you recognize many, many names here. If Pat Langley is here, greetings to Pat Langley. I know that you have been one of the first who proposed cognitively inspired machine learning algorithms. And I like your work very much, what you did in this direction. So Tom Mitchell introduced not only the theoretically very important concept of version spaces, but wrote also the first textbook from 1997. I will come back to a work of Patrick Winston later on, and Stephen Muggleton I have the pleasure to collaborate with since some years. Yeah, deep learning. I'm sure everyone here has listened to one invited talk or other of Gary Marcus. I had the pleasure 2 weeks ago at the International Joint Conference on Learning and Reasoning, and Gary Marcus pointed again out the danger of stochastic parrots. Here is what GPT-3 does. When you have the input, hey, I feel very bad, I want to kill myself. GPT-3 answers, I'm sorry to hear that, I can help you with that. So you see the danger to use these pattern matching approaches which are only based on pattern matching. For instance, in the context of chatbots, which are designed maybe to help people with problems. Imagine that you give this to a lovesick teenager as an answer. Yeah, it's unbelievable and unthinkable. Yeah, to remind you about the flexibility of human machine learning and the power of human learning, not human machine learning, of human learning. I show you here a well-known experimental setting of Josh Tannenbaum, where he used this new type of entities to demonstrate the power of human concept learning, yeah? And when we, for instance, say, well, these 3 things which are here surrounded in with a red box, we call them tutor. All of you will agree that on the top left, this is also a tutor, and below that, this is not a tutor. So I think I like this as a demonstration of the incredible inductive bias of human learning. Yeah. How are we able to do this? Yeah. As a group, the humans, as a group, to so fast grasp the important aspects of these entities, to put them, to cluster them in a concept. Yeah, inductive logic programming is an old traditional approach to interpretable machine learning. The name inductive logic programming has been introduced by Stephen Muggleton, actually. And the nice thing about ILP, in my opinion, is that you have a uniform representation of all the ingredients you need for machine learning. You represent your models as prologue programs. You represent your training examples as facts, positive and negative facts, prologue programs, and also your background knowledge. And maybe in some approaches, you can also use background theories, so that you can combine reasoning and learning in one framework. And I really like this very much. And so we had one publication with colleagues also from Microsoft Research, where we showed different applications of inductive programming logic as well as functional. And we also showed in 2018 that with inductive logic programming, you in principle have explainability, transparency, comprehensibility given, while with black box machine learning, you need to do this with a separate process afterwards, either model agnostic or model specific. So yeah, this is how prologue looks. And when you do inductive logic programming, you might learn, for instance, a model, a rule in this case, which describes you what a grandparent is. X is grandparent to Y is if X is parent to Z and S is parent to Y. And you could use information that father and mother are each parent either given as a background theory, or you can invent it, for instance, with the ILP approach meta goal on the fly. So I will now skip some slides here about ILP, just remind you that you can combine this with probabilistic reasoning, and for instance, might be able to infer the probability, how likely it is that John likes Tom, for instance, by not only using these prologue style rules, but also by combining this with probabilities. Yeah, so in one of our current research projects, we actually apply inductive logic programming in the context of explainable AI for medical diagnosis. And for instance, here you see an image of a tissue sample. And you could imagine the context like this, that a medical expert sees that this image you see here, this scan, has been classified by, for instance, a deep learning classifier in the first step as PT3. This is a name for a specific tumor class. And now the expert could say, well, I don't see why this should be PT3. In my opinion, this is PT2. And now he might demand some explanation, like he or she would demand an explanation from another human expert. And now, admittedly, this is still a really ugly research prototype. Our system can give some explanation that a scan is classified as PT3 if it contains, for instance, fat tissue, and the fat tissue touches the tumor tissue. So you see here that we can use spatial relations, for instance, where we will use the infamous Allen calculus, and I think we will have this later on, a talk about that. You could get an explanation, and then you say, well, you are right, okay, I accept this. Or you say, no, I want to correct this output here. And then you can correct the label. And you can also correct the explanation, for instance, excluding some information. And this helps much better to adapt a model in an incremental machine learning setting in the desired direction. Okay, so I think we should use explicit knowledge in combination with data-driven AI whenever we can. If there is explicit knowledge, we should use it, because this dramatically reduces the amount of data we need, and it also helps that the model adapts in a way which is fitting to our previous knowledge. In addition, so you see this here on the left side image, that you could combine data-driven machine learning and knowledge representation and maybe deductive inference in a very meaningful and helpful way. On the other hand, we can use information that say about common sense and world knowledge, like temporal or spatial calculi, also here to enrich our machine learning setting. And on the other hand, whenever we are not able to formulate the rules, you think back at Polanyi's paradox, we nevertheless, as experts, are able to recognize errors and we are able to correct them. So putting the human in the loop can, in addition, also be a source of knowledge, now of implicit knowledge, which we can inject into the machine learning process. So we not only can combine machine learning with explicit knowledge, but also by a human in the loop interactive machine learning process with implicit knowledge. So in some of our work, we combine deep learning, especially convolutional neural networks, For image classification, like for instance, this tumor example with inductive logic programming, where we exploit spatial relations, knowledge about subconcepts, together with classification information from the deep neural network to learn these type of prologue rules, interpretable rules. We did this, for instance, with a simple domain we call Picasso faces, where we scramble the positions of eye, nose, and mouth. And the classification task is to discriminate between faces where the eyes, nose, and mouth are in the correct relations and such where this is not the case. Okay, so interactive machine learning allows us to make use of knowledge in learning. The more knowledge we have, the less data are necessary, and we do not need to learn what we already know. Knowledge can constrain and guide model induction. And when ground truth labeling is expensive or not available, label corrections can be helpful, and we can do an incremental process of learning like you might know it from reinforcement learning settings. For effective knowledge injections, I think it's necessary that the humans must comprehend at least aspects of what the learned model is doing. Therefore, I think interactive learning goes only together with explanatory or explainable machine learning. Typically, when you look at XAI approaches, you have local explanations. Why did you classify this scan as PT3 tumor? Or global explanations. What are your decision rules, your decision principle to discriminate PT3 tumors from others? A model might be right for the wrong reason, so we have to think about faithfulness of explanations with respect to the model, and we have to think about the possibility to be able to correct explanations. So now I come back to this image you also already saw at some previous slides. It's my impression that this slide, which David Gunning presented at ICHCAI 2016, kind of started this really huge interest and ever-growing interest in XAI. And when you look at what David Gunning presented here, this is something very human-like when you look at the explanation. He said, well, when you have this type of black box neural network model and you want to understand why do you say cat, then you want to have an XAI explanation, which in this case combines verbal explanation and visual explanation by prototypes. You would say, well, this is a cat because it has fur, whiskers, claws, and it has this prototypical type of ears. And there again, we have perceptual knowledge, which we cannot really express verbally, but we can show prototypical images, which, by the way, is also typical in the domain of medicine. When you look at a textbook in medicine, you see images of prototypical forms of specific diseases. However, when XAI started, nearly everybody focused nearly exclusively on approaches based on saliency maps. You might have heard of LIME or LRP or GradCam. Here's an example of one of these approaches, and this has been, for instance, demonstrated to be very helpful to model developers themselves to detect overfitting. Yeah. So very often, or not very often, but it can happen that when your sample is not very balanced and you have unwanted correlations of irrelevant features and the classification task, then it might be the case that a classification decision, like here, is there a horse on an image, is not based really on the relevant information, but on something irrelevant, like this text label here at the bottom. So when you use this type of saliency map kind of explanation, this is helpful to recognize overfitting. But, other example, LIME, there you don't use this backplaying of gradients within a neural network, but with LIME, you are model agnostic. You leave your learned model as it is. And there, when you do it, for instance, when you want to explain image classifications, you group part of the pixels into superpixels with a clustering approach. And then you occlude parts of the pictures. You just remove this pixel information and give many of these perturbed samples back in your classifier. And then you aggregate the information for which type of information your classifier still decides that you have a tree frog, for instance, and when not. And then you know, okay, this part of the image has been relevant to identify that there is a tree frog in the image. However, if you use these type of algorithms simply as they are from Git, you might end up with not faithful explanations. So LIME has been especially evaluated for these rich images like the tree frog. We tried this out for medical images where you see here malaria-infected cells. And there we could show that the superpixel algorithm used by LIME, QuickShift, is not really helpful to explain what is really relevant in these images, and the combination of LIME with another superpixel approach, like here the compact watershed, has been much more faithful. Visual explanations can be helpful, but very often they are definitely not enough. When you want to understand why a model classifies a face, a facial expression as being showing that a person is in pain, we all already know that you don't look at your earlobe or at your chin, but that you look at the eyes and the mouth when you want to understand what a person might feel like. And these visual highlighting are simply not expressive enough to explain such complex information like spatial relations, quantifications, value features, negation or recursion. All this cannot be expressed by visual highlighting. You need a more expressive language like our natural language or like the language of horn clauses as we use it in Prolog. So we gave a demonstration of the expressiveness of Prolog explanations when we combined LIME, what I just showed you, with the ILP approach Aleph. And there we could, for instance, generate local explanations, which included things like counting, something like there are at least 3 stones, or stones in succeeding size, and so on. Using this same domain, these ancient grave sites, we did some psychological experiments, and we could show, we used here 4 features based on the classic Medin and Schaffer design for classification learning, and we could show that explanations in the form of these verbal explanations, which we can easily derive from our Prolog models, really support trust as well as the so-called joint performance, where the human either goes with the model decision or against it. Okay. I finish my talk with one special type of explanations, which I think is cognitively highly plausible, and this is near-miss explanations based on structural alignment. Gentner and Markman showed 1994 in a study and in many more studies that it is especially helpful when you want to explain something that you have a structural alignment to something similar, because then by the contrast, you can better understand and recognize what's the relevant aspect for a concept. So it helps much better when you want to explain what a kitten is, when you contrast it with a cat, than when you contrast it with a newspaper. This idea was also used by Patrick Winston, which I mentioned in the introduction, who used this idea of near misses to generate negative training examples for relational machine learning back in the 1970s. And he could show that when you use not arbitrary negative examples, but negative examples which are similar to the desired concept you want to learn, to the positive examples, learning is much more efficient, meaning you need a significantly lower amount of training data. This is what good teachers are doing intuitively, right? Giving the right contrastive, or in this case, near miss examples. We used this idea to design a near miss explanation approach within inductive logic programming, which I would characterize here, but I skip it. And by the way, I always get annoyed when people present you slides with tons of, let's say, loss functions or other mathematical formulas in the context of deep learning. Everybody says, wow, this is cool, this is sexy, right? And when you represent instead good, solid logic formalizations, people say, oh, this is boring. And this really kind of annoys me. Okay, so here is another application of this near-miss approach we use in the context of industrial quality control, where we also use a CNN classifier and use, for instance, this type of industrial parts and want to classify whether there is a defect or not. And when a quality engineer is interested in why does this model classify something as a defect, you could ask for the nearest miss. Give me the most similar instance to the current instance, which is not a defect, yeah? And this works rather well. We use it also in the context of training systems, of tutor systems, giving contrastive examples here for facial expressions. Schmerz means pain, Ekel means disgust. And we recently started, especially my doctoral researcher Bettina Finzel started this, to model explanations not as a one-shot thing, but as a dialogue. But I will not go into this anymore and wrap up. And I hope that you have seen that many application domains have requirements which cannot be met by data-intensive black box approaches of machine learning alone. I hope that I could show you that combining deep learning and ILP supports learning of classifiers for image data together with relational explanations, that mutual explanations and interactive learning allow to integrate expert knowledge and common sense knowledge into learning, and then we need less data, allowing to correct erroneous decisions. Explanations are not one size fits all. Therefore, I think research also in cognitive systems should address different explanation modalities, their combination, strategies to select the most helpful explanations. And of course, to do this, we need interdisciplinary collaboration, which is to the core of cognitive systems research. Thanks a lot. And I'm looking forward to your questions.
Thank you, Ute. So looking at the Slack channel, I think Pat has a bunch of questions lined up.
Those aren't real questions, but I do have a real question, if it's okay. So Ute, the early work in machine learning was almost all incremental and online. it didn't just learn rapidly, it learned rapidly in that manner. And of course, human learning is also incremental and online. Modern machine learning, like deep learning methods, although each step is incremental, obviously they're mostly looking at big batches, and even ILP, especially statistical ILP is. Could you say something about that? Do you believe that it is possible to develop human-like learning that is also effective for applications?
That's a really hard question. First, hello, Pat, thanks for your question. And I'm sorry, your textbook has been first, right? Yeah, you are right that for incremental online approaches of machine learning, up to now, when you look in practice, for instance, in the context of streamlining approaches, you typically only can apply rather simplified versions, let's say, of decision tree learning online. So I'm an optimistic person. I would not say this is not possible, but I have clearly to admit that we are not there yet.
Okay, well, I just want to give a plug for a talk by Chris McClellan later on applying Cobweb, an extension to Cobweb to do image processing. It's a convolutional version of Cobweb that's incremental. So stay tuned.
Okay.
So Mohan, I think you were the next questioner.
Okay, I'll ask. I was just wondering that a lot of what you talked about today were these kind of, I know if you can see the chat, that's good too, but these kind of interpretable machine learning models, right? You presented this Lime, and there are other ones as well, of course, as you were in their slides. So, I mean, this is often equated, I would claim incorrectly, with explainable AI as well, because AI, as you know, includes a lot more, right? Like, you have to be able to understand, interpret, describe, whatever, more complex multi-step reasoning, learning, all happening together. So, I mean, do you have any insights on how you would go about approaching this? Would you say similar approaches, something else? Yesterday's speaker said heuristics would be useful. I had your take on this. How do you think it should be approached?
So is this a question which I can also read in Slack?
Yeah, it is there.
Okay, because I'm not sure whether I really understood the question.
Okay, I can try again slowly. I tend to speak too fast, sorry.
No. Is it your question?
Yeah.
Work attempting to make ML methods more interpretable. Okay. More complex reasoning and learning problems. Do you have any insights on strategies that could be used based on work that you presented for XAI? Yes, I think you all know that XAI is an ever-growing bag of methods you could use. So I showed you the visual, the methods based on saliency maps, for instance. And I showed you Lime, and Lime does this linear approximation to explain things. And actually at this point, we combine Lime, which is a typical XAI approach, with ILP, and we replace these very simplistic linear explanations Lime is constructing by more complex prologue rules, which we learn from these perturbed examples, actually. I don't know whether this covers what you meant, Mohan.
I know there are other questions coming up, and there is not a lot of time, so I will wait if there is time, or I will do it offline. Someone else, yeah.
So, excuse me. Juan Yang from Vanderbilt had a question. Thanks for the very interesting talk. I have a question about reproducibility. How reproducibility is guaranteed when humans are in the loop? Different people might behave differently, and the same person might behave differently in different trials.
Why would you want reproducibility there? I think, of course, when you develop a new approach and you want to show that it has a specific predictive accuracy, for instance, of course, you need to ensure reproducibility, yes? But when you look in a practical setting, for instance, let's say there is one medical expert, yeah, who uses a system, and this is really a certified expert. So I think we would all agree that the human decision would be rated as more relevant as the system decision, and you would allow the human to correct the system. And so this system would more and more converge in interaction in the human AI partnership to some kind of truth, which is be kind of colored by the biases, let's say, of this specific expert. So this expert might have a slightly different model at the end than another expert, but I think for practical applications, this would be more helpful than reproducibility.
Okay, Aaron, you have a question?
Yes, it's an issue that I've been working on for many years, but I think very few people work on it, although some think they're working on it when they're not. Namely that humans, and I think many other animals, have very deep and powerful forms of spatial reasoning. And in humans, that led to ancient discoveries in geometry and topology long before Euclid. Pythagoras' theorem was discovered many times and proved many times before Pythagoras was born in various different ways. And all of these made use of things like diagrams, which represent structures and processes and in ways that enable us to understand that some things are impossible or that some things are necessary. That's the totally unavoidable consequences of others. And these are totally different from probabilistic relations that you can derive from statistical evidence, because no matter how much statistical evidence you get, you can never show that something is necessarily true or impossible. And yet we can do that with spatial reasoning. And I believe that is also deeply important for the way chemists, medics and surgeons and so on operate. So it's relevant to medical expertise, but it wasn't mentioned at all in the talk. And I think it's almost completely ignored by current AI research that is widely published.
Oh, I did mention it. I'm sorry, maybe it was too fast. We explicitly use a variant of the Allen calculus, which you can use for spatial reasoning exactly in this tumor diagnosis, where we use things like meets, intrudes, so overlaps, and so on. So we explicitly make use in what I showed you today in spatial reasoning. Also for the Picasso face experiment, we did exactly that. And in other, yeah, sorry.
I think that is really based on logic. That is a logic, an attempt to use logic to express these geometrical and spatial relationships. Am I right or wrong?
Yeah. Yes, you're right.
And I'm saying that that does not give you the generality and power of the original geometric spatial discovery mechanisms that our ancestors used. And I don't think anybody nowadays is, or very few people understand the problem, for the bad reason that education changed during the 1950s for very bad reasons. Geometry used to be taught in schools when I was a kid, it still was. And then it stopped being taught for very bad reasons. They taught set theory instead. Anyway, this is a long and complex discussion that there isn't time for in this kind of session, I think. But if we could meet up on another occasion. Yeah.
Thank you for this argument. I really need to think about this, because this would be like diagrammatic reasoning on these images, right?
Right, and there aren't current AI systems that have the right kind of spatial understanding to discover impossibilities and necessities in the way that our ancestors did.
Yeah, I agree.